The magnetic field does not only affect the wires with electric currents. A free charge moving in air or vacuum also interacts with magnetic fields, causing a force that deflects the charge. The charged particles may be positively charged like protons or alpha particles. They also can be negatively charged like electrons, cathode rays, or beta particles. The effect of a magnetic field on a positive charge is the same as that on a wire with an electric current, given by Fleming's left-hand rule. For the negative charge, the effect is opposite to that on both wires and positive charges, and it's opposite to that given by Fleming's left-hand rule. And now we will study in details the electromagnetic force on a charged particle, and this is by Fleming's left-hand rule. Let us start with the case of a positive charge. Any free moving charge like alpha particles normally move in straight lines until an external force is applied on it. In this case, a magnet is there, taking place in the pathway of the positive charge. The dotted black arrows show the direction of the magnetic field lines, which is into the page. In this case, the path of the charge is not a straight line anymore. The positive charge experiences a force applied by the magnetic field. The direction of this force is also given by Fleming's left-hand rule. If the first finger points to the magnetic field direction into the page, and the second finger points to the direction of the conventional current, which is the direction of the normal motion of the positive charge, in this case from left to right, then the thumb shows the direction of the pushing force on the positive charge, in this case upwards. The magnetic field shown by these two magnetic poles, where the north is out of the page and the south is into the page, can also be represented on plain paper the way shown, indicating that the direction of the magnetic field lines perpendicular to the plane of the page into the paper. This will push the positive charge upwards. To describe in details the new path of the charge in the presence of the magnetic field, we first need to draw it. The charge moves in straight line before it enters the magnetic field. Inside the magnetic field, the charge takes a curved path. Of course, this is due to the electromagnetic force on the moving charge inside the magnetic field. After the charge leaves the magnetic field, it continues moving in a new straight line after it has been deflected. We can describe the motion path of the charge in this case as upwards, curved path between the poles, perpendicular to the magnetic field lines. If the charge was negative, it will be logic that the force will be opposite to that of a positive charge, if magnetic field direction is the same. A simple non-scientific way to deduce the direction of pushing on a negative charge is also by Fleming's left-hand rule, but taking the opposite of the final direction of pushing shown by the thumb. To describe the motion in this case, the best words are downwards, curved path between the poles, perpendicular to the magnetic field lines. The following example shows a positive charge moving straight to the right, before it interacts with the given magnetic field. The dotted black arrows show the direction of the magnetic flux lines. Since it is a positive charge, Fleming's left-hand rule will be directly applied without reversing any results. If the first finger shows the direction of the magnetic field to the top of the page, and the second finger shows the direction of the conventional current, which is the direction of the positive charge as well, the thumb will show the direction of the pushing force on the moving charge, in this case, out of the page. Sure, if this positive charge is replaced by a negative one, the same rule is used, but the direction of pushing is taken as the opposite of that of the thumb, and it will be into the page. There is still a case where a moving charge will experience no force, even if it is moving in a magnetic field. The dotted arrows just appeared show the direction of the magnetic flux lines between the poles. If any charge moves in any direction parallel to the magnetic field lines, no electromagnetic force will be applied on this charge. Here we will discuss the factors that affect the amount of deflection by electromagnetic force on the charge. This positive charge will be deflected upwards by the interaction with the magnetic field of the magnet. The direction is given by Fleming's left-hand rule. If another charged particle with bigger mass but same speed and carries the same amount of charge passes through the same magnetic field, it will be deflected less than the lighter particle. This indicates that as mass of the particle increases, the amount of deflection will decrease. this charge will also be deflected by the magnetic field. If the charged particle shown is replaced by another one with higher speed but same mass and carries the same amount of charge, it will deflect less than the slower one. This leads to a conclusion that as speed increases, the amount of deflection decreases. This third case shows our normal charge that is deflected by our magnetic field. On replacing this charged particle with another one, which has the same mass and moves with the same speed, but carries a larger amount of charge in coulombs, the charge will be pushed with greater force and hence deflects more. Now summarizing the factors that affect the amount of deflection. The amount of deflection by electromagnetic force applied on a charged particle depends on: Number 1. The mass of charged particles. The smaller the mass is, the more deflected one, if speed and the amount of charge are equal. Number 2. The speed of charged particles. The slower is, the more deflected one, if mass and amount of charge are equal. Number 3. The amount of charge carried by the charged particles. The greater the amount of charge is, the more deflected one, if mass and speed are equal. Number 4. The strength of the magnetic field. The stronger magnetic field causes more deflection. Before we finish this part, we can conclude that electromagnetic force is applied on a particle only if this particle is: Number 1. It must be charged. No force on a neutral, uncharged particle. Number 2. It must be moving. No force on a stationary particle. Number 3. Motion is not parallel to magnetic field lines. Number 4. Enters the magnetic field. No force on a particle away from the magnetic field.